ago. This is important information to tell you where the coronavirus came from. The Pope, Bill Gates, Adam Schiff, and George Soros. So now you know this woman is running for Congress in California, down in LA. So sadly, I will not be able to vote for her. But anyway, that's important information. And
I'm going to be announcing.
They were going to have the NIH official on 5 Sunday talk shows, but Pence's office took over to control communications, so he was asked to cancel all those. So they're still deciding what message they wish to tell us. This is about what I'd expect out of them. The Senate is passing a bill to hand out money to help people replace Huawei equipment. So they're trying to get all the Huawei equipment off American networks that might carry important traffic. So we'll see what comes of that. The FCC is mad at all these telcos who sold your location data. So they're talking about finding them something. And again, we'll see what comes of that. Pretty much everybody is selling your personal data these days, and there don't seem to be any effective rules against it, although the new California privacy rule, which doesn't take effect for 4 more months, might help somewhat. And this guy wants to kick Jack Dorsey off of Twitter and take over Twitter, which is not a political stunt. This is actually, many people have called for this, including some people I respect, because Jack Dorsey has decided he's going to spend half his year in Africa and be an absentee CEO, and that is considered poor practice. Not very many people want to have a CEO that isn't around full time. There's a guy in San Francisco, a company quietly building rockets. There is a rocket contest from DARPA to build a rocket quickly and ship it off someplace with almost no warning. So they built this thing in Alameda, and they're taking it up to Alaska to send it off. So there is a group called Astra, a company making rockets near San Francisco. Might be fun to learn more about them. There's a Magento exploit. Magento is a very common payment platform, and this one lets you spoof an order so you can send a payment notification callback request without real payment. So you can reroute payments to an account under your control. But sounds pretty bad. There is an update, but it's interesting stuff. And I had another one in my news. Yeah, this one was, this guy made a vulnerable WordPress website. Apparently there are people who will do pen tests for $15 or even $5. So he made a vulnerable website and paid for 3 of those and made a video of it. And as you might imagine, they are terrible. It reminds me of Gregory Evans, a notorious security fraudster years ago, who would take money for pen tests, and what he would do is run Nmap and then send you the Nmap report, and that was his pen test. So anyway, that's kind of what you might expect from these folks. So we're here with Heap exploits, and down here, we're here. Heap overflows today, and then next 2 weeks, we have guests coming, which will preempt class. After that, we'll resume again. So we talked about these before. Heap overflows, you can see the memory map of processes with info proc map in GDB, and you will see something like this. You have a stack and you have a heap, and the heap is used for unstructured chunks of data. Whereas it does not have this last in, first out structure like the stack. So it just has chunks of data, and before each chunk of data, there is some metadata. And in the simplest heap used by a lot of Linux distributions, you just have a couple of size measurements and a couple of pointers to the next chunk and the previous chunk. So this is a doubly linked list where you can hop forward with the next pointers and hop backwards with the previous pointers. And in Cisco routers, there is a process called check heaps that actually checks every few seconds to make sure that the heap is intact. But there is not such a structure in most operating systems, so you can corrupt the heap. In Cisco routers, you cannot corrupt the heap for more than a few seconds unless you find a way to stop that process. So in a simple example here, you define data structures, and then you, so on the heap, there's a structure called data and a structure called FP. And those are just structures until you create instances, and you create instances with the malloc command. So you declare a data structure and a FP structure here on the heap, and then you copy data into the first one, which is a string, and then go jump to the second one. So this is a contrived example, which makes a heap overflow have approximately the same result as a stack overflow, because you have a string variable followed by an address, and the address is then used to redirect execution. So you'll be able to insert data, which is too big, and have some of your characters go directly into the EIP. So this is a very simple example that makes heap overflows as simple as stack overflows. So if you put in a little bit of data and look at it, you'll see your data there and the pointer down there, and all you have to do is make it longer, and then you can take it over. So let's, I think I'll just demonstrate it all in a row later. Well, let's take a look here. So that is ED. I think that's ED 204. That's heap, right? So anyway, we'll do demonstrations a little later. Anyway, so the stack contains stored EIP values at the end of each stack frame, which means just overflowing a string variable, you can take over the EIP directly. Normally, you cannot do that on a heap unless you're lucky enough that somebody actually stores a pointer on the heap, like that last example. In most cases, there's only data on the heap. However, when you rearrange chunks, when free is called, you do write operations, which require fixing those metadata pointers, and that can give you control of a write operation. So that's the problem with heap exploits. You can't directly control the EIP. Instead, you're going to get a write operation. Now, you can still take over the machine with a write operation, but it's a little bit tougher. So here, for example, if this node in the middle is freed, then the forward pointer from this node has to be redirected to this node, and the backward pointer from this node has to go change to point back to that. And that means if I was able to overflow data here and change the metadata here, I'd be able to control a write operation. And that's what happens with most heap overflows. So then you just have to find some place where you can write that will eventually give you EIP. And obviously you could aim for something on the stack. You could use the global offset table, which is what we've been doing so far in this class, the destructors table or C library hooks. Any of those would be fine. The add exit structure or any function pointer, those are things that would be ways to get yourself into the EIP. So let me do the Cahoots, and then we'll take a look at some of these demos. So here's the Cahoots. With only 2 of you, it's not going to be a competition, but still you might get some reinforcement from answering the questions. I don't know where everybody is today, but they missed the Cahoots. All right. All right, I guess that's got to be both of you. All right, which command becomes an arbitrary write after a heap overflow? It's free. Not allocating a new chunk does not require a write. It's freeing a chunk that requires a write. Which command reserves space on the stack? Okay, once again, malloc is what reserves space on the heap. This is how you reserve space on the stack. We've done it before. You just define a character, and that reserves it on the stack for that local frame. Which command creates a new chunk on the heap? That's what malloc does. Good. All right. And which command shows the location of the heap? info proc map is the one that does it. There is no info heap. All right. All right. Which command moves EIP to an attacker-controlled value in a Stack Overflow? Okay, it is return. Return is what takes the value on the stack and jumps to that address. All right. And which command allows direct control of the EIP after a heap overflow? Okay, none of them. That's the problem. You do not get direct control of the EIP easily after a heap overflow. All right. So Chun and Carol are the winners today. All right. And so let me go to the demonstrations here. I'm just going to demonstrate a couple of projects, which is going to be here. And okay, 205 for starters, and then 206, at least the first part of 206. So for 205, we've got this vulnerable program, ED205. So let me bring it up here in my cloud server. Okay, so there it is. If we less ED205.c, we can see the source code. Oh, I don't have less, fine. I'll just cat ED205.c. All right. And so I've got libraries, then I've got the data in FP, the same thing we looked at before. There's a no winner function and a winner function. And here we've got allocate a data string and a pointer on the heap, and then we leave. And it's going, here you set the pointer to no winner, and here you execute the command that you set the pointer to. So it will always print the no winner command unless I can overflow it. So to overflow it, I can just run this ED205, I think. All right, it wants a string, so I put in a string. All right, and now I just need to put in a longer string. Let's just copy and paste a few of these. And at some point, it should be enough to cause a segmentation fault. So I am able to cause some kind of crash. So now I just want to run it through GDB. All right, and I can do info proc mappings. Then I'm going to have to start it. So let's do disassemble main. All right, so here we are in the main function. And you can just look at the right to see what we're going to do. Print something and exit. Perhaps I can use source code. I can see the source code. Oh, that's good. I don't even need to use assembly line at this point. So let's just list 1 to 40 and get the whole source code here. And here's main. So it prints a message about the help message, and then it allocates a couple of things. And here is where it attempts to use that pointer. So it's going to, well, this is where it assigns it. Now here is where I'm going to get a chance to overflow. I'm going to get a chance to copy something that came from input onto a string variable on the heap, and it's going to overflow and cause this to point to an unexpected place. So I'm going to break at line 33. Now I can run the program, and I'll put in AAAA as the data. And now, if I do my info proc mapping again, I can see that the heap is here at that address. So I can x/40x at that address. And I can see here's the A's I put in, 41, 41. And here's the pointer to continue, 8048 F6. If I want to verify that, I can go back here. I can look at my disassemble main. I'm looking for 84 F6. Actually, it's going to be no winner is what's going to be there. Yep, that's it. That F6 address is equal to the no winner address. So that's where it's going to go. So I can see what I have to do. I have to put in a whole lot more A's. So let's run it again with a larger number of A's. 1, 2, 3, 4, 5, 6, 7, 8. And then maybe some B's. Something like that. And start it again. And now examine the heap again. And it looks like I still don't have enough. Here's my E's, and I still haven't got enough to get down there. I need 1, 2, 3, 4, 5, 6 more groups of 4 bytes. So I can put 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and then something like that. And when I run that and examine the heap, it still didn't make it. 47, 47, A, B, C, D, E, F, G, yep, but I made it right up to the edge of it. So the next 4 bytes, B, C, D, E, F, G. So I have H's? I didn't have H's. Okay, so next 4 bytes are going to hit the pointer. So I think that'll do it. So all I need to do is disassemble winner. All I need is this address right here, 0804 84CB, and that's what I need to put in. So let me just get this template. That's the prefix right there, and I'll quit the debugger. And now I should be able to quit and make an exploit. So it's nano demo 1.py. That's going to be shebang user bin Python and print. All right, and that's getting kind of long and annoying, so I'm going to just make that into prefix. And then I'm going to print pre plus. Now I need that address, which I've forgotten, so I'm going to go back in the debugger and get it, unless it's, oh, here it is. There, winner starts at this address. So I need to put that in my exploit. That's the address I want, so that should be here, \x cb \x84 0408. All right. If I've done everything correctly, this will cause an overflow. So let's chmod +x demo1, check it. It prints all those characters and then some unprintable junk at the end, which is what I expect. And so if I run ed20, what is it, 204.6? It's 205. All right. And then I put in that string of demo. And now I get level passed. So that's what I wanted. I did manage to control the instruction pointer and get back to the desired location. So now I've got a few more to do here, which you can do online. So here's one that does the same thing with one of these online processors. Here we put in hexadecimal. So if I put in 41, just 4 A's here with 4 41s, and I send this, then I can see what happened here. I run this program, ed205.2, and it's a 32-bit program. Here's some of the source code. So I've got a winner function that will print out a flag, and a no winner function that won't. Here's the place where it allocates a couple of data items on the heap and does exactly the same thing. It's the same program we just exploited. It has a string copy of something that came from us into a location on the heap, and then right after it, it uses the next few bytes on the heap to determine the instruction pointer. So we should be able to exploit it the same way. So here is the memory structure. Here's the heap. The heap is here at 56, 55, 9000. Here's a printout of the heap. Here's the 4 A's I just put in. And here's the pointer to the no winner function, which I should be able to see I guess I didn't print out no winner, but I can tell from 56 that that's pointing to code. So this looks like the pointer I want, and I'm going to change that pointer to this, which is where winner is. So I need to make a longer thing than 4 A's. So just like before, the way I recommend doing this is to use a text editor to prepare your exploit. So here I'm going to get rid of the hyperlink processing there. Okay, so here's 4 A's, and it looks like I need quite a few more, so I'm going to put in a lot more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 perhaps. Let's see what that does. Oh, I don't need to really save it for what we're doing here. All right, so this one has got more A's. So there they are. And it looks like I did clobber the number beginning with 56. And if that's true, I did get a segmentation fault and it went to 41, 41, 41, 41. So some of my A's controlled it. It looks to me like it was these, like I have 8 A's too many. So if that's true, let me get rid of 8 of them. 1, 2, 3, 4, 1, 2, 3, 4. And then try putting in something characteristic like this, 31, 32, 33, 34, which I'll be able to spot. Go there. And now, too long must be an even number. Okay, I fouled up my string. 41, 41, 41, 31, 32, 33. Well, how annoying. All right, let's just try undoing what I did here and going slower. 1, 2, 4. Let's try that one. All right, that one worked, and I hit 41, 41, 41. Okay, then let's change that last 41 to 31 and see what that does. Oops, I keep hitting save, but I don't need to save it. When you get in trouble, small changes are always the best. So now it complains, okay, changing it to 31 is somehow causing a problem. All right, what have I done wrong here? All right, that works. Let's go change this to 42. All right, now I have 41, 41, 41, 42. So it's looking pretty good. So I should be able to make 42, 43, 44, and 45. And that should target the EIP exactly. All right. And again, I have somehow fouled up the length of this. Well, I don't know why my demos are fouling up so badly. Let me just try and get where we need to go. This one works. And as I've often said, when you're in trouble, you keep one that works and don't change it. So this one works, and I can hit 41, 41, 41, 42 in the EIP. So let's keep the one that works, and let's try getting where we need to go, which is here to the winner. This is the address I'm trying to hit of the function. So to put that in, I need to put it all in backwards in hex, %90, %57, %55, and %56. That's what needs to go instead of these last 4 characters. So let's see if I can do that. I don't know why I can't make these smaller changes I'm trying to make. I'm sure somebody watching this video will be able to see what stupid mistake I'm making. But that should run the winner function. And print stuff, it goes down here. It quits and exits normally. And at some point, it should have printed out the result of running the winners function. The flag is breakpoint 1, mapped address spaces, execute the GDB command, and here's the address 5655 5700. That doesn't look right. All right. So what did I do wrong? 56, 55, 57%, 90. Somehow went, it's off by one, 56, 55. It's off by one character. 56, 55, 57. The percent 90 just seems to vanish, which is mighty screwy. All right, well, I'm totally falling off my track here. Let me go to my solutions and get the ones that works. So here's the one I did to target the EIP before. And let me see, this is, let's see if I can, I don't know why I'm losing my mind, but perhaps it's because I'm sick. So I'm making some mistake and I can't see it. Here's the one that worked before. If I can get this thing to work. All right. So here, I just send up that string, which has just got a bunch of 41s and then 31, 32, 33, 34. That's what I tried to do several times here. There it is, 31, 32, 33, 34. And there it goes into the EIP. So that means I control the EIP, and all I have to do is put in this address, 5655, 5790, and that's what this is. Oh, it's the percents. I forgot. This is a thing in which you put in hex directly. You do not put in the percents. That's why it was not giving me the expected results. So anyway, that's what does it here. Now it's going to run, and someplace in here it's going to show the results. Yeah, now it's going to show you a flag and show that you won. So what you want to see. So it's not supposed to be too difficult, but it's easy to get confused, which is what happened to me there. So let me try another one. We'll see if I can do this one right today. So 205.3 is just a 64-bit version of the same thing. So that's down here. And again, you put in 41, 41. I'll put in a few of those just to see what's going on. And I have the same structure. It's the same program, just recompiled for 64-bit. So here it copies something into a string, and here it jumps to a pointer that came after the string. The heap is here at 55, all this garbage ending in 7,000. Here's the structure of the heap. Here's the 4 A's I just put in. Here is the 64-bit address I'm able to target. I want to change that address to this address. So first I have to hit that address by just trying longer and longer attacks until I get in. This is the one that worked after I got in. A lot of 41s, and down here I just put 31, 32, 33, and so on to target it. And this one does hit segmentation faults at this location, and should have had the 31, 32 stuff show up somewhere, but maybe I can't find it. Here's the 41s. Here's the 31, 32 up to 38, which is good. And when it continues, this is a thing to be aware of in 64-bit processors we talked about before. If it was a 32-bit processor, we would see this number, 31, 32, 33, 34, appear in the EIP, but on a 64-bit processor, it crashes before that point because this is not an allowed address. Remember, all the real addresses are only at the top and bottom of memory, not in the middle like this. So it's worked, but we can't see the address going straight into the RIP, as we might expect. But you can see it is in a couple of the other registers here. So now that we can control it, all we have to do is insert the address for the winner, which is this address ending in 4960. And that's what I've got here. This address ending in 60, 49, 55, 55, instead of those other ones. So when you do that one, it's going to run. And when you get to the continue part, it's going to show a flag and show that it worked. So that's the that's 205, which is this very simple case. Now the more interesting one is 206, where you have an overwrite. And here There are 3 parts here that I can do today. The 4th part I'm still having trouble with. I think it was only partly finished and I shouldn't have published it yet. That's why some students are asking me for help on number 4 here. And I have a solution, but it's kind of a mess. And I need to work on that. So if you're struggling on that, just wait a little bit until I get to update this project. But let's talk about the general case here. You've got 206, which is here. And if I run my ed206, it now wants 2 strings. So it wants AA and BB, and then it finishes. So if you look at the source code, it defines a structure which has got 3 integers in it. And let's go up here, there. You define an internet structure which has an integer and a character, and here it defines 3 of them. So I1, I2, and I3 are those structures. Notice it does not contain a pointer to anything, so you allocate a few of them and you copy data into a couple of them without limiting its length, and you are able to overflow. But the overflow is not going to hit a pointer, which goes straight into the EIP. It's more like much more realistic heap overflow. So if we run this one, there is a point at which you see a crash, and you can just use longer and longer strings, and this one here is long enough. If I run this one, that string right there, ed206, on that one, I get a segmentation fault. So this string is too long and it overwrites the metadata, which causes the next write to do the wrong thing. And that's all we need. So if we GDB ed206 and then run with this as data, it's going to crash. First, I better figure out how to put in a breakpoint. If I list, I can see it here. Okay, so once again, I'm here in main, and here I define these and I write to this one, then I define it and write to that one. The first one is going to work even if it overflows, but the next one I think is where, oh, here's the string copy. Okay, the 2 string copies are going to work. I think it's going to crash when it does the second string copy. So let's put in a break at 36 and see if that works, or a break at 38. All right, so let's run with that long stuff that's going to make it crash. And it made it here without crashing. If I continue, it crashed before it made it to 38. And now if I do a backtrace, I can see I was in main at line 36, and then I crashed in some internal C subroutine. So when it tried to do the second copy, it failed because something about the broken metadata from the first one made it crash. And if I do examine 10i from EIP minus 10, that will just show me the instructions, except I have to have EIP. That'll show me the instruction pointer. This is the instruction it attempted to execute where it crashed. That's what that little arrow means. It was trying to move the contents of EAX into the address pointed by EDX when it crashed. So all I need to know is the registers. And EAX contains 4747, EDX contains 4646. So the command I executed to get here was this. So it's A is 41, 2, 3, 4, 5, F is 46, and G is 47. So I now control an arbitrary write operation where I can write the value in EAX, which is this value, and it goes into that address. So all I have to do is replace these G's and these F's by a location I want to go to. And let me go back to my instructions here. So you want to choose a write address. So all you have to do is the same thing we've done before. You use your obj dump. The program ends with an exit, so we can target this as the address, and we can disassemble winner to find out what address to put in there. And again, we can redirect code to the winner function. So there should be an exploit doing that called H11, this is it, A, B, C, D, E, and the two addresses in reverse order. And so that I've already put in here. Let me just get out of the debugger. If I ever get out, okay. And if I cat H11, it's here. So if I run ed 206 on that should do it. Now you have a winner. So we managed to take over control of the thing with just a write operation, which is a small step of what we've done before. And so, looks like there's a problem with my image there. I'll have to fix that later. I was trying to improve this project, but my image didn't get the right permissions on my server. In any case, so there's a 32-bit server to run here, and there's only one dirty trick here. You're running essentially the same program. So if you put in some A's and some B's here, and then debug it, you see the same source code essentially, and this one ran successfully. So you have to make it longer and longer until it crashes. So I've got some solutions here to work from. All right, so this one shows how we control it. Let's try that one. A, V, all right. So this one sent in a long series of A's and then some B's and C's, and the second parameter is 1, 1, 1, 1. And so here it's going to have a segmentation fault. The backtrace shows which line it failed at. And here we see the command that it failed at, which was move EAX into the address pointed to by EDX. And the EAX is the 1111, and the EDX is the CCCC. So this string, I control the ones and the C's are what I want. So I just need to take the winner address and the exit address and put them in here backwards. And this time I need those percent. So I was trying to put it earlier for this kind of structure. So that is one, which looks right. Remember this address that we're trying to execute here, the exit ends in 5C. And here is that address backwards. And if you try this one, it looks good, but it fails. The reason it fails is because the 5C command does not get into memory. The 5C byte, because 5C is a backslash, and a backslash is a control character. So if you want to make a 5C actually enter memory, you have to have two 5Cs. The first backslash tells the bash command processor not to interpret the next one as a control character. So when you need a special character like 5C, you got to put it in twice. And that's one of the many little dirty tricks. And now this thing should run and show you the flag and such. Then it will crash again, but it does run correctly and show you a flag. And there's just one more down here that I want to talk about today, which is this one here, 206.3, is just the 64-bit version of the same thing. But it turns out to have some problems. So if you do this, that's why I added a couple more hints here. So again, the same story starts here. You put in short things and it just works. You have to put in longer things to see it crash. I had to go down to the L's, counting up through the letters, 4 letters at a time. And now it will crash. And when it crashes, you will see the command. Here's the assembly code near where it crashed. Here's the command it crashed on. Now there are a few things that are a little weird here. It crashed on a somewhat strange command that's taking the high bits of D, EDX or RDX in this case, and putting it in the address pointed to by RDI. So you might try to figure out how to achieve your goal by doing this, but notice that the next command is much simpler. Move ECX into RDI. And what's going on is the reason this one crashed, trying to write into an address pointed by RDI, is because RDI is full of characters we fed in there. 4B and 4C are like the J and the K in that long string. So we have caused a crash that will not really crash once we put realistic values in here. So once we put in more intelligent values that aren't obviously invalid, this command will succeed and it will proceed to this command anyway. So we can only pay attention to this command to plan our exploit. And this takes ECX, which is the lower 32 bits of RCX, which we control, and it puts that in RDI, which is another register, and we control that entire register. So we can write a 32-bit address in any register we want, and that turns out to be all we have to do. The addresses of the functions really only have 32 bits they're using. Here's the address of the exit function. We don't need to write the nulls because there will already be nulls there. And the winner function is similar. It's actually only using 32 bits. So it turns out to be pretty easy to do, but there are a couple of problems. One is you have a lot of null bytes. And if you try to write the null bytes, it won't actually do any harm, but it will pop up an annoying PHP error message. But the other more important problem is, again, bad characters. If you try to build it directly, you will get this one here, which has those addresses in it. Here's 400,676. This is 400676. This is one of those addresses. And here's the other address that we have to get to, which is the address of the exit function, which is 600BE0, 600BE0. And again, I have to put a 5C in before the 60. That's the trick. If you don't put that in, it will crash because the 60 is a special character. It's a backtick, and you have to escape it. So today I added a couple of hints here. That's why I've changed this project a little bit to make it a little easier. 206. And that's these hints here. You don't need to send the null bytes, and you have to use 5C60 to move the 60 into there. So that's how you get a solution that will actually work. All right. So that's as far as I wanted to mention. This 206.4 and 206.5 are kind of messed up, and I'm going to work on them and improve the instructions here. Some people are struggling with them. I'll have that done in a few days here. Are there any questions about anything? Go back to my Zoom here, and the chat with nothing whatever in it. No questions yet. Okay. Anyway, that's all I wanted to show you for today. I'll stop the recording and I'll leave the share going for a little while in case anybody has questions.